do a more involved example. Let's say we want to compute the area under f of x is 2x squared minus x plus 3 on the interval from 2 to 4, and we're going to use the right endpoint approximation. So we know we have to fill in, what is delta x, so that's b minus a over n, so delta x is 2 over n. And so then our x sub j term in general is going to be a is 2 plus j times delta x, so j times 2 over n. So we've got these two things written out. So now we can say, well, what is our right endpoint approximation? So this formula right here, r sub n is delta x, 2 over n, times the sum from j from 1 to n of f of x sub j, 2 plus 2j over n. So at this point, we want to plug in 2 plus 2j over n into our function here. So this is going to be a little bit messy. We're going to get 2 times, so 2x squared, 2 times 2 plus 2j over n squared. I'm going to put all this in big brackets, minus x minus 2 plus 2j over n plus 3. So this is what our summation is going to look like here. Now, if we simplify this, there's a little bit of algebra to do. I'll let you check for yourself that if we simplify this down, we end up with 8j squared over n squared plus 14j over n plus 9. And what I'm going to do now is on the next slide, I'm going to rewrite this as 3 separate sums. One with sum of the j squared, one is sum of j, one is sum of 9. So this is, so the first one I'm going to do is I'm going to have the sum of the j squared. So I'm going to move out 8 over n squared. So 2 over n times 8 over n squared times the sum j from 1 to n of j squared. Now I'm going to have the sum over j and move out of 14 over n. 2 over n times 14 over n times the sum j from 1 to n of j. And then we just have a sum of 9. So we can move that outside. 2 times 9 over n times the sum j from 1 to n of, we can just say that's the sum of 1. So what do we end up with here? 16 over n cubed times the sum of j squared. Where's our power sum rule? It's this one right here. So n times n plus 1 times 2n plus 1 over 6 plus 28 over n squared. The sum of the j's is n times n plus 1 over 2. And plus 18 over n, and we're just summing up 1n times, that's n. So what simplifies here? Those cancel, that cancels. And at this point then, what we are really interested in is we're interested in the limit as n goes to infinity of this whole expression. So that's going to be limit as n goes to infinity of 16 times n plus 1 times 2n plus 1 over 6n squared plus 14 n plus 1 over n plus 18. So a little bit of thought should say, well, this is equal to 18 under the limit. The limit of this is going to be 14, and the limit of this ends up being 16 times 2 over 6, 32 over 6. And so the answer is 16 thirds plus 14 plus 18. So I guess that ends up as 112 over 3. So this is how we can use our approximations and summation notation and our power sums in order to quickly compute the area under the graph of this function. So let's just take a moment to acknowledge that let's just comment on what we just did here. So this is a rather non-trivial thing that we did. So the graph of the function looks like this. We just found, so this was our f of x, we just found this area. It's area under a parabola. I don't think that our high school geometry classes gave us formulas to calculate out area under parabola. So this is non-trivial when compared to the previous case that we did, finding the area of this triangle. That's something that we can do in high school geometry. But here we have a new problem that I don't think we can do without resorting to these calculus techniques. Okay, so one more thing for us to do. Here is just a comment that sometimes our limits are difficult to compute. Sometimes this becomes computationally tricky to do. So one last example. Suppose that we have f of x is equal to sine of x. Suppose our interval is pi over 4 to 3 pi over 4. So basically what we're looking for, there's pi over 4, there's 3 pi over 4. We're looking for that area right here. So if we want to do this, same thing as before, delta x is going to be b, 3 pi over 4, minus a, pi over 4, divided by n. And this ends up as pi over 2n. X of j is the left endpoint, pi over 4, plus j times delta x. And if you write out what is our r sub n here, it's delta x times the sum from j from 1 to n of sine of pi over 4 plus pi j over 2n. And so if we try to evaluate, or at least we try to take a limit here, this ends up being difficult for us to do. So what is sine of pi over 4 plus pi j over 2n? That is going to be, right now it's going to be difficult for us to do. We could take a stab at that with using angle addition identities and stuff like that. But right now it's going to be tricky, but in future classes, in future sections, we're going to have more to say about this. Okay, so I think this sets us up well. We are all ready for, so for those of you, let me just say a couple words here. For those of you who have seen this before, we're doing all of the preliminary work in order to be able to get in to start talking about what are definite integrals. So you know what a definite integral is. You're able to compute them because you've seen calculus before. We're going to say the definite integral is going to be computed in this way that we've just been presented. And that will be something we'll do in section 5.2.